Welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with 3,000 people working on topics spanning from bioeconomy to materials science, built environment, transport, and digital systems. Specifically, our computer science department works on applied AI projects for the benefit of society. And we organize the weekly Learning Machines seminars as part of our Center for Applied AI Research. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. I should also say, make sure to check out the collection of great talks that we have on our YouTube channel. Note that there will be no Learning Machines seminar next week, and next talk will be Tomasz Trzeciński from Warsaw University of Technology on October 13th. Today, I had the pleasure to introduce Jörg Tiedemann, who is a professor of language technology at the Department of Digital Humanities at the University of Helsinki. He received his PhD in computational linguistics from Uppsala University in 2003. Working on bytext alignment and machine translation. He then worked as a postdoc at University of Groningen on question answering and information extraction. Some of his research interests are multilingual datasets and data-driven natural language processing. And currently he's working on representation learning and natural language understanding. The topic today is translations as semantic mirrors. Representation learning with multilingual data. And with this said, I will hand over to you, Jörg.
Yeah, thank you very much. I try to share my screen, so I hope you can see my screen now. Hope you can also hear me well. Thanks for inviting me. Thanks for having me here. It's a great pleasure, and I hope you can enjoy the talk at least a little bit, even if you're not coming from NLP. I will talk mainly about one project that we are running here, which is called Found in Translation, FoTran. It's a long-term project that started some years ago and mainly goes about representation learning from multilingual data, as the title suggests here. So I will talk about a couple of papers that we have published, but not mainly looking to all those different kinds of details from the papers, but also giving a high overview of what I think is important to discuss. And I start with just giving you also a little bit of my view on natural language processing. And just because maybe not all of you are from NLP, from the NLP community, I give you my view, and we can also come back to a discussion, if you like, on those kind of ideas that I put here for presenting what natural language processing is actually addressing, what kind of way it works with language signals. So if you look at NLP, from my point of view, of course, we all know that we have some kind of language signals that we can observe. So we have text or speech or even gestures and sign language. And that is a completely observable signal that we can see. Humans can receive that kind of signal and we can process that. So natural language processing, looking at those signals, then has certain tasks that would be typical signal processing tasks. So if you look at, for example, text to speech, so if you have automatic speech recognition or text to speech as a task, then this operates on observable signals, translating between those two. Or if you want to translate between gestures and sign language and text, then you would also have some kind of signal processing, basically what you will deal with, what you would have to deal with. So in some sense, this, of course, has a lot of complications, but we still have a very observable problem here, which can be fully supervised. So you can record the signals, you can train, for example, a model that then make the translation between those different types of or modalities, and then you can optimize for those settings. And the complications are, of course, that they're not completely compatible in the form that they're uniformly mapped to each other, so that you, in some sense, you have a loss of information if you go from one to another, so that you could talk about some kind of lossy compression, for example, if you go from speech to text and certain features are not preserved in the text and vice versa. So that's that part. And then the next kind of level would be to go into what I call here now a structure space. As we know, there's a certain structure in language signals as they combine to each other, combine compositionally. There's a lot about structure that you can learn and observe in language signals. And then you have to address questions about morphology, for example, or syntax, or also some kind of semantic functions that you would like to analyze. So in this kind of, there's a lot of previous work from linguistics, of course. Experts know what kind of structures can be observed in languages. There's a lot of debate still, of course, going on, but supervision can be provided by experts who have analyzed the language structure and those kind of underlying principles of language as a signal or communication tool. So this kind of level is quite well known for a long time, also in computational linguistics, and computational linguistics has traditionally really addressed a lot of those problems by building models that can parse a text and provide then the adequate analysis of that text, for example. Similarly, for speech, you could go into phonetics and phonology. And then once we're now talking about natural language understanding, in many cases, we might still actually move in this structure space and seeing to, can we understand the structures of languages, but typically we want to go further into a space that is completely hidden. So we don't have really access to the intended information or knowledge that someone tries to communicate using language signals. So as we humans use language as a kind of general purpose tool for communicating and explaining things, debating and touching everything that we know about the world around us, then this is very non-accessible what kind of representation would be behind this kind of information and knowledge, and how that then maps into, for example, the language signals that we use for communicating. So it's quite a different problem from understanding language from a structural point of view. All of this then needs some kind of representations, and this comes in clear in the talk also, so that I want to look at representations. So if we want to now go from the signals that we can observe into something more abstract, then we need some way of representing that abstract information. So in the structure space, I now put it in terms of linguistic representations. That can be any kind of representation that you might have in some formalism for grammatical structure, for example, or maybe some vector-based representation as well. And then again, the same for the meaning space. So there we also need some way of representing the information to make it accessible, or to work on top of those representations. So the essential point of natural language processing is to be somewhere on those different levels and finding a way of mapping between observable signals and then producing those kind of representations that we can operate on. So coming to the kind of opposite task, where we not want to just look at the signals and then analyzing it or understanding it. If we come to natural language generation, then the first step of defining how to get representations is actually essential. So without having representations, we cannot even start doing any kind of generation task. You need to have some way of representing linguistic signals or meaning in some way before we can actually generate anything that is then the kind of language output that we would like to use for interaction with humans, for example. So in some sense, I still see that NLP is mainly focused on finding the ways of good natural language understanding and finding good mapping from language signals into some representation space. By the way, if you have any kind of questions in between, you can also ask me in between. So from a different kind of point of view, I already started about talking about compression. In a sense, those different spaces are quite different in the way that the linguistic representations basically try to compress information that we observe, or the signals that we observe. We try to find a good way of finding structure that can be used compositionally and can be used productively. So some way of compressing the information that we see in the real world, but representing it, for example, with a very compact grammar. So typically this kind of lossless compression includes all the information about the signal that we have, but trying to see whether there's some important structure that we can see productively being used. So I see this as kind of lossless compression that you try to make into having a language describing it with very compact grammar, for example. The other side, I would put it into quite the opposite, saying that if we have some kind of meaning and knowledge, this is anything that we want to express about the world or something around us, we use languages for efficiently communicating about that knowledge and that information. But in order to make that in efficient and also in a limited amount of time, we use very lossy compression techniques, not expressing everything in detail, because that would be a never-ending stream of signals if you would have to explain all kinds of details. But instead, there's a lot of implicit information, but also things that are not explicitly expressed at all, but need to be inferred by the listener. So there's a really big kind of difference between those different levels. We compress kind of a large information space into something that can be observed in a stream of signals that we can listen to or read, for example. So in that sense, also maybe this addresses the question about over-parameterization of deep learning models, for example. If you think in this way, then maybe those models are not over-parameterized, but they need this larger space to actually express meaning and representations with lots of parameters. So we need a much higher capacity of a model instead of compressing it down into some bottleneck structure. But we can discuss that later if you want. So for me, natural language understanding in some sense tries then to go back to the meaning space. And if you think about this kind of compression idea, then it would mean that we now have something that has been compressed with some kind of loss of information. Now we have to find a way of decompressing it. And because it's lossy, we have to find some way of inexactly, but approximating the best kind of decompression without having all the information available. So the observable language code that we have needs to be decompressed into what was the original meaning or the original information that we try to retrieve again. So from that point of view, actually this part should be called decoding, because now we have a language code that we can, or the human language code that we can observe. And now we have to decode it into something of the information that has been represented by that code. Funnily enough, I mean, if you look now at the typical implementations, now this part is encoding. It's called encoding. So we typically talk about an encoder that tries to encode information we observe into the machine readable code used in a model, for example. But conceptually, I would say it's rather a decoding step. Another point which is quite important is I don't believe that it is possible to have any kind of supervision, proper supervision, in a way that you can define how a meaning representation should look like. This defines the knowledge as the information that humans use for producing communication signals. So that kind of complex information that we gather from experience and from observing the world is hard to describe with kind of symbolic supervision, for example, or some kind of supervision is really difficult in that sense, but it will be rather indirect always. So it becomes really an unsupervised task in the end, or kind of implicit supervision. And this is the next point. So if you look at how this is approached, then this really becomes this kind of indirect supervision that now becomes such a powerful tool. So instead of going from some kind of supervised material where we can learn the mapping between two different sites, we use some kind of proxy tasks. So there's tasks that we know that humans can do and on top of language and communication, and we use those tasks as proxies to learn those representations that basically give us the mapping between language signals and meaning representations. And again, so nothing really new here, but you know that we now have this wonderful toolbox of deep learning and neural networks. They are very operational, so you can use that kind of standard approach that throwing some kind of your favorite neural network architecture on that kind of problem, using this as the black box that you put on top of this mapping that you need and feed in some input and some output and let the system decide how to process the data. And hopefully it will learn implicitly that kind of mapping that you need. So this is very successful and powerful. And as we know, it's quite amazing what you can do. So application-oriented work using that kind of black box is very is the standard anyway nowadays. And you can also say that if you're interested in application only, then maybe you don't have to care about knowing more about that black box as long as it really works for the task that you're interested in. So if you feed in lots of information coming as an input and the right output comes out of the system, and this really provides everything you need in your task, the performance goes up by doing some kind of tweaks and tricks, then this is the perfect solution for an application-oriented work that we are, of course, very much interested in. But of course, as we are researchers, we try to ask questions, and then one amazing part is, of course, that you don't really understand how this is going on. Why is this work? How does it work? What is happening inside of that black box? And this is, of course, the whole community is working on understanding the black box, analyzing it, trying to see what is happening inside and what kind of architecture is supporting what kind of abstraction and what is an abstraction anyway. So there's a lot of questions coming up with this approach, which makes, I think, NLP nowadays into a science which is quite close to maybe cognitive science, but also general linguistics, where you have a black box of a human. You try to understand how does that human really make very difficult decisions and complex reasoning. And now we have an artificial kind of black box, which we try to analyze and understand how does it do certain tasks that we didn't expect it to do. And that's basically a big question that many people try to tackle, and also we in our project try to look at quite a lot. And now going back to what FoTran and our project is supposed to look at mostly. So one of the questions, of course, what would we use as kind of proxy task? So what is a good way of learning those meaning representations? And the amazing thing is, of course, that very simple things like masking out some text, some words, and predicting it. Those kind of proxy tasks already bring us a long way, or give us quite reasonable mappings that we would not expect easily from that simplicity of the task. So in many cases, most of those seem to be more on the structure space, I think. So would explore the kind of structural properties, linguistic properties of language, and how they are compositionally built up, how they are used productively. But we know also that we can touch very much into the meaning space, saying that we can get abstractions that go beyond just understanding the linguistic structure and understanding how language is used as a communication signal or a kind of a framework for communication, but really having that kind of mapping going to some semantic representations that we didn't expect it to do, which is quite interesting how that really happens. But what we asked in the project that I'm presenting here today is that maybe it's interesting to look at some more advanced kind of tasks and seeing whether that also leads to different kinds of representation that can be learned, different kinds of ways of abstracting away information that you see as an observable signal, and how can you analyze what is really the difference when you have a different kind of task that you're looking at. And for me, coming from a background where I've been working a lot with translation, machine translation, this is kind of my big hammer that I'm putting on any kind of problem that I see. But if you see translation as a task for also a human, then this really naturally combines both of these sides of natural language understanding and natural language generation, which is an interesting thing that you don't have in many other natural tasks that you can observe. So you can see that a translator basically has to perform this kind of function of mapping from some input signal, interpreting it, and finding some way of understanding it, and from that generating another version in a different language. And the nice thing about this is that now we have naturally occurring signals from both sides, so the input part, but also the kind of recreation in a different language. You can think of asking someone to rephrase something that you don't understand. So if people don't understand what someone says, then you say reformulate it. So that would be another way of forcing a way of giving you a different view on some kind of information. And translation does this naturally without asking people to reformulate. But instead, this kind of translation task really tries to reformulate the input information, but just in another language. So it gives you another view on what that information should contain.
Can I ask you a question?
Yes.
Can you see some differences in different from language similarity? I mean, if you translate to Nordic languages, there are great similarities, and one could argue that the signal would be perhaps not entirely forcing the internal representations to actually understand the language, but it would be sufficient to just change some spelling and some very superficial changes. Can you see this in your work?
Yeah, my next slide is basically about that. So the basic motivation for our project was that exactly the point that you're raising here. So if you do something that is very closely related, then a system which basically tries to minimize effort would probably not go very far in understanding. So the main question that we also raised here is that how much does linguistic diversity and distance between languages influence or has an impact on a system making an abstraction? So this kind of figure just tries to illustrate that. So assumption is, of course, would be that if you have something that is more distant, then also a system needs to make a bigger effort to really parse and understand and really get the knowledge or the information behind the input to produce an adequate translation. Whereas if you would have Swedish Danish, maybe you can just replace some characters very kind of systematic. So you make a shortcut and don't go into any kind of meaning representation, for example. So I think this is exactly what you asked about. It's kind of the motivation of the project is that we want to push for highly multilingual models, seeing that we can push the coverage of the systems, making it actually harder for a system to translate all those. You should translate between all kinds of languages. And we would like to see whether this then pushes the system to make strong abstractions. And that's the hypothesis that was put into the beginning of one proposal of the project and was the main idea. We want to study that, see how the kind of the limit looks like. I will unfortunately not present much about that, but I can tell you it's much more difficult to show that this is really happening than I would have expected in the beginning. So we don't clearly see that more abstraction is happening if we increase, for example, the language coverage in such a system. But we do see tendencies, but it's not as clear-cut as I would have liked to. And we work on something. I will also present a little bit about the ongoing work that we have there. Yeah, it's harder than expected. But again, so this basically was the motivation for starting FoTran. Not only that translations mirror information, but also that different kinds of translation give you lots of different views. And if we have lots of different views and very distant views on the same kind of thing, then we hope that we get a more abstract and language agnostic kind of representation that touches the meaning level much more than other kinds of approaches. So this is FoTran. So what I had very quickly, so I tried to still keep time as much as possible, but let's see that there's a lot of kind of dirty work that needs to be done first. So I have just a couple of slides about that, and then the second part would be more about analyzing the internals of translation models and showing if there's anything interesting coming up. Okay, something crashed on my machine, but you still see my screen, I hope. So what I think most people might know me for, so if you know me at all, then there's probably the collection of parallel data that I've been trying to push for a long time. The Opus collection is probably still the biggest collection of translation data in many languages, publicly available. And this is a great resource and of course necessary kind of fundamental work that needs to be done. You need to have the data, and Opus gives you a large coverage, for example, of different languages in the world, which is exactly what we need. And there's, for example, now also a compilation into a data set that I call the Tatueba Translation Challenge, which makes it a bit easier to really access everything, which is prepared for making it straightforward to use it in training and testing. So you have already predefined train dev test splits. So you have a large language coverage, like over 500 languages there. You have consistently labeled data with the language flag that you might want to use. And you can use it, of course, as a machine translation benchmark across many of those languages that certainly have not enough resources otherwise. So if you don't know about that, I would ask you that you could check it out and give it a try. So it's a really nice resource. Around the whole kind of Opus infrastructure, we built actually an ecosystem that includes lots of things which are not as relevant for this talk as maybe some other things, but so as we're also looking into practical development of machine translation, this gives us the tool for having the data that can be systematically applied to training machine translation models. So we can systematically train over all kinds of language pairs. We can train multilingual models, but we can also provide the models, for example, for people who want to use it in production systems or for further development. So we try to be as open as possible and integrate things into Hugging Face, for example, so that people can write their 3 lines of code to access our systems or our models. Also recently, because it became a bit overwhelming, so many models, so many different language pairs, so there's now also this, what I call the leaderboard, so you can also follow, for example, the different benchmarks that you can put on top of machine translation models and see which ones are performing better on certain benchmarks. So you can choose and select and also inspect the translations that can be performed on different data sets and for different language pairs. So also, again, this kind of background for you, if you are interested in machine translation, check that out. But coming back to FoTran and the ideas about multilingual models, so then just a quick introduction of what we try to look at with the multilingual settings. So maybe many of you are familiar with the typical multilingual translation model, a sequence-to-sequence model based on transformers with cross-lingual attention. And what you can do is, for doing it multilingually, you can just basically type put everything into just a basic training set, and for making it possible to decode into different languages, then you can have a special label that makes it possible to, in a completely shared model, to also generate different kinds of output languages. So that would be an easy way of using your favorite, the standard kind of architecture, and you just make it multilingual. What we also would like to look at is, so how much do you want to balance between language agnostic or shared parts of the model and language specific components. So there's also a trend that you can modularize neural models, and this is in the same direction. So we have been for a long time already working on that architecture where you would have a certain kind of shared layer between all languages, and then you would still have language specific components that then read, for example, specific languages and produce certain other languages. And you try to combine them all together into a complex architecture where everything has to be pushed through the shared components in the middle, which then hopefully become something more abstract across all different languages. So that's the kind of attention bridge model that we have been presenting in some papers, and we are currently working on scaling it up for many different languages. So the idea would be that, as we are interested in what can be learned by machine translation models, we are basically interested in those shared layers, where you can say that is this becoming some kind of more abstract representation or not? And we can then test that with, for example, benchmarks that many of you are probably very familiar with. So can you benchmark some kind of different NLU tasks, for example, and see that you get different kinds of abilities, performances from different setups. So what we are working on is still also development. So first, you need to really make it scale a lot. So we promise to go to hundreds and maybe thousands of languages. So we need to have a nicely parallel training setup where we can run over many GPUs at the same time and distribute the training steps on lots of different nodes. Now, the complicating part here is that if you want to really scale it up in this kind of a modular setup, then distributing it over different nodes is not as straightforward as just doing, let's say, multi-node training with the same architecture. But now we have different subsets of encoders, decoders being present at different nodes. So you need to find a way of nicely distributed over different nodes and make the communication in a way that the whole system as a whole works, but that you have a nice decomposition into different sub problems on different machines. So we are working quite hard on making that scalable and quite transparent, so that you can just say, okay, now allocate 100 nodes and distribute our problem here with 600 languages and then train the whole system over the entire data set. So that's what I basically said already. So now we have those problems where you need to minimize the memory footprint, or you have to look at the distribution so that this is a good distribution, that you use the memory available on all nodes, that you have also internode communication that really doesn't make any kind of interruptions between the entire training process and someone is waiting for a long time to get, for example, some kind of scores aggregated. So we need proper distribution and rotation. We need to properly distribute also the kind of synchronization steps and so on. So just wanted to let you know that we are working on that, and we will, of course, also open source all those kind of developments so that this could be useful maybe for others. And then other kind of design principles are also quite important for us, as now the picture somehow only showed very generic image that you would have maybe one layer in the middle, which could be this language agnostic so-called attention bridge, but you could decide on different amounts of shared layers and different amounts of language specific components. So we would of course like to also explore how much do we want to share and how much do we want to keep as more language specific, or maybe language group specific or language family specific information. So again, there should be flexibility in deciding how to set up the architecture. So I used quite some time on that, but that's fine. So the second part, what I wanted to talk about is more some work that we have done on analyzing neural machine translation and properties of a system and representations that they produce. So this will be quite different from the other parts, which are a bit more practical about development, but this is more about looking intrinsically into a system and trying to understand what is happening and how does it differ, for example, from other kinds of training objectives, for example, language modeling tasks. So this comes from several papers, and I took some interesting things from here and there. Let's see, I hope I can present that in a reasonable way. Looking at, for example, different ways of how self-attention looks like, then looking at contextualization, how do kind of contextualized embeddings look like in machine translation models, and then also understanding how embedding spaces are built and how they differ from language model embedding spaces, for example. So first study, just briefly mentioned, I also do that rather quickly. So one thing that we observed is that, and that was early on, that self-attention, for example, is surprisingly peaked around certain positions. So very common what we see, and that's maybe also for language models, is that the self-attention patterns, they don't distribute that you get information from many different kind of places, but instead they seem to have a very strong focus on some parts of a sentence. And it's much more strong than you would expect with a freely learnable kind of architecture where they can basically combine information from all different places. So this is something quite striking that you see patterns like this coming out of translation models where, for example, very strongly the system looks at the same position, so identical, or just maybe the words before, the words after, and then you also have a strong focus of some attention heads going to the end or the beginning of a sentence. So those patterns are so strikingly heavy that you could see that it is actually quite painful for a system that it has to learn this by heart. It seems to be very consistently just having those kind of information needs from those different positional places, relative positions. So what we did is we said that, so let's say, why do we want to make it hard for a system to learn those patterns? Why can't we just give them as fixed given attention patterns to a system? And just for testing whether this is actually a good assumption that we can replace it by something that you give as a prior information, we made those tests where you replace 7 out of the 8 attention heads with fixed pre-given patterns. This is quite a busy picture here, but just giving you the overview of the results. And it has 2 scenarios. One would be a more kind of high resource scenario, and the other one would be a low resource scenario. And what it basically says, so now we replace those attention heads with the patterns that you see at the bottom of this slide here. So reflecting what we have observed by just manually looking at the attention patterns, but saying that, okay, we distribute information that you can take from previous words, next words, and the previous context, the next context with some kind of decay, and the end and the beginning of the sentence. Those are just not trainable at all, but just given. And you can see that from the results that this does not really actually, this really does not hurt the system. So it does not seem to be a problem to make that replacement, and the freedom of learning those attention patterns is not really necessary. And that's the same for the high resource setting, but especially in the low resource setting, the interesting point is here that because you make it easier for the system that it doesn't have to learn this by heart, in low resource settings, you actually gain from this additional prior that you give to the system. And you get consistent improvements by taking something that seems to be generally important for such a model, give it into the system as prior information. So this is basically the takeaway from here, that there seems to be self-attention patterns seem to be quite peaked around certain positions. And you could even use that for predefining information. And now after this study, I think many models actually use that for efficiency reasons and for treating, for example, longer sequences. As you already know now how the attention patterns should look like, you can process longer sequences without overwhelming the system by different decisions. Okay, but looking at that also, that might raise some questions of how much contextualization do we actually need if we only look at certain positions. So how much do we actually need the connections to different contextual positions in a sequence? So then we asked quite a lot of questions on how to look at that, how to measure contextualization inside of translation models, but also in language models. And there's this work here from 2019, where different measures are suggested, where you can measure contextualization. There's self-similarity, where you measure how similar is a contextualized word embedding in different contexts. So you can sample certain words, or for words that you have in some kind of test set, you can measure how different is the representation inside of the model in different contexts. So that's the average kind of similarity between those different contextualizations. And then you can also, another measure would measure the distance from a contextualized embedding to the mean embedding of the sentence. So if you would have some kind of mean value for the entire sequence, how different is each position from that mean value? So that's the intra similarity that we can measure. And another question is that, for example, how well does the system really use the available embedding space? And you can measure the property of isotropy. So how uniformly does the system or the embedding space really use the entire space? So what is the expected distance that you can get from randomly sampled contextualized words, for example? Is that more a narrow space that you actually just use, or do you use the entire space of all the dimensionality that you would expect that randomly sampled words would be quite distant from each other? So you can also calculate some average similarity to see how well does the cosine similarity that you can see between different words, how is that restricted to a certain space or part of the space that you're actually using. And the main idea was, so I think it was just observed that you, in many cases, maybe just use some kind of cone-shaped space, but not really the full sphere of every kind of opportunity that you have in that dimensionality. Then you can use that for also correcting this self-similarity measure, because that really influences how much cosine similarity really expresses distance and relative distance to other places. And just jumping into some pictures here, as I said, so if I'm taking too much time to all of this, you can stop me at some point also to leave more room for discussion. But so what we want to see especially is also, is there a difference? First of all, is there some effect of being anisotropic in those embedding spaces that you learn, or do you use the full kind of sphere? And is there also a big difference between language models and translations models, as we were interested in seeing how do they differ, and does that tell us anything about why they perform differently? So here's a comparison which might look a bit weird. So now, as we all use the same kind of transformer architecture for everything, it makes it possible to compare, for example, translation models to language models, as now also in both cases we have the same transformer architecture. But of course, now we have, for example, BERT, as this one model uses 12 layers, but in the typical, or in the case that we used here, the machine translation model only used 6 layers in the encoder, for example. But so one takeaway from this picture is that this looks at average similarity now, so the measure of isotropy. You can see that surprisingly, a lot of average similarity can be seen, especially at the later layers in the BERT model, for example. So you can go way above 0.5 in average similarity, which is not expected, as you would say, that this really narrows the cone that you, or the part of the space that you're really using. So it seems to go up all the way from like the first layer until almost the last one, and then it drops a little bit. So many of the things that I'm showing you now, actually we don't have good explanations and reasoning for that, but it's just to showing you that this kind of thing is happening. So if you do cosine similarities on embeddings from different layers, you should probably be aware of that. There's a certain reshaping of the embedding space that could influence the measures of cosine distances that you, or similarities that you measure.
I have a question.
Yes.
is the goal of this, is that to have some calibration for the similarity score, or is it some assumption of that it's useful to use the whole embedding phase? Or is there, are there arguments for actually using the whole embedding space?
Yeah, so it's not a clear-cut answer that I can give you. One thing is, of course, calibration. So you would calibrate the cosine similarity because you know that this you kind of, the shape is actually squeezed together. So you might also think of that if you would compare, for example, cosine similarities on different layers and you're not aware of that fact here, then this kind of non-calibrated distances would give you different results, except of that there's maybe not a difference that you should observe. So I think this recalibration could be a good argument if you really use the representations for some kind of further inferences or further decisions. So that's one thing. Another thing is, of course, you could argue that this might show that you really over-parameterize, so that you don't need that kind of dimensionality because now you're using some kind of different part of the space. And maybe there's on certain layers over-parameterized setups, and that could also lead to some architectural choices and saying that, okay, maybe we can prune things away, and as we know, pruning works. And this could explain why pruning works, as certain things seem to be unnecessary in the dimensionality. I think that could be one of the things as well. Does it answer your question?
Yes.
Yeah.
Thank you.
Yeah. Let's say
follow-up question, if that's okay. So, I mean, I haven't seen any more work in the same area for a few years, but a few years ago it was some interesting work in terms of having non-Euclidean representations for the embedding space, for instance. So, do you know if the same thing would apply also for, let's say, a Poincaré sphere, as you would see here for the Euclidean spaces, in terms of anisotropy?
Yeah. Yeah, I don't know. I'm not sure. I can imagine that you see a similar effect also in other, but I would not have the answer. That's actually a good question. So no, I would not have any good intuition either.
I was just curious. It's I haven't seen it in a few years. Kind of more work in that area, but it was quite interesting a few years ago, at least. So I just died off. I don't know.
Yeah, no, we didn't explore anything in that direction either. So I would not know, but yeah, good point. Should maybe explore that also a bit more.
Can I ask a question?
Yeah.
I mean, this might be a bit broad, but like, is there a theoretical reason for cosine similarity to make sense in like bird-style contextualized embeddings in the first place?
I don't know what to say about that. Well, it's a widely used distance metric that you use for, I think most things we really don't have good answers for. So it's just for practical reasons that we are relying on certain things that we know how to define and how to use. I would not really know if there's good theoretical reason for doing it. Maybe someone in the audience knows more about the theoretical foundations of neural networks and how they are trained, whether cosine really makes sense at all. So I can ask the audience.
I mean, maybe it was a bit of a leading question. I mean, in my mind, I mean, if you take word2vec, for example, there's a very tight coupling between like cosine similarity and because the vector is kind of directly you can if you squint a bit, you can see the like embeddings as representations of distributions or yeah. But in contextualized embeddings, they aren't I mean, they are, but in a different way that, to my mind, makes it less reasonable to employ cosine similarity.
Yeah, I don't know. But of course, I would assume that while you try to still see that also this kind of at the position is not really a word embedding, but it's more condensing information from the context. But how to really treat that and compare that to other kinds of similar contextual embeddings is, I would not have a good theoretical answer to that. How that should be treated.
Okay.
But as you know, so if you think of classification task or any kind of task where you on the top layer, you just take the embedding of some kind of special token and you use some kind of cosine similarity and do all kinds of fancy things on top of that. I don't know if there's always a good theoretical explanation or kind of evidence that you can do it in a way that practically works quite well. It's kind of because it's the same if you have this CLS token and you take that for making some kind of decisions and predictions and maybe use something similar to cosine similarity, then this is exactly what people are using. But why this is the good? I mean, this is one reason why we also want to investigate what is happening with those. If you really do it, is that maybe problematic or not? And you can see that at least for different layers, you have quite different shapes that you build up, and you probably should be aware of that because people do a lot of kind of comparisons what is happening on different layers if I use it for classification, for example. But if you're not aware of this, then maybe this is really affecting your result quite a lot, and you should recalibrate or not. But as I said, no good kind of theoretical answer for your questions. If you have any, please let me know. Yeah.
I have some ideas, but
okay,
maybe later.
Yeah.
Thank you.
I'm not sure how we'll do this with the remaining parts here. So, but I can also jump more to the end and leave more time for discussions, as I've been taking quite a lot of time. But because I presented the self-similarity and interest similarity also, that might be interesting to look at also from the point of what is happening on different layers again. So here's a plot that compares again the same BERT model and some MT machine translation model, the encoder only. And then we can see that something that is probably expected is that the self-similarity goes down from layer to layer in the language model setting, which means that it becomes more and more contextualized. So it makes sense. You're mixing more and more information from different places, even though maybe not that much, but you contextualize each position more, which means that it's not becoming like a word embedding anymore, but more a mix of different kinds of things from the sentence or the surrounding context. The interesting thing here might be that it seems like machine translation models stay more close to some more very lexicalized representation in the beginning layers, and it only drops very dramatically at the end. So the contextualization seems to happen very much at the last two layers and even maybe just at the last layer. So it seems to be much more focused on the lexical information, let's say, or maybe I don't know how to explain it exactly, but I think it would not really increase the contextual information that much, so that that the similarity goes down between different usages of the same word. So that's again a bit of an interesting difference between MT and language models. What that now exactly tells us, I don't know exactly, but at least it shows you that this is happening on different layers. So contextualization is not necessarily linearly growing, but it can also have different kinds of shapes. Also, the interest similarity is actually quite interesting that this is quite high. So we're getting a quite a blurred picture over the sentence, that the information probably is encoded similarly in all different positions, also showing that the contextualization is there. But this is very similar between language models and translation models, maybe a slight different shape, but I don't know what that means and tells us. So now you should tell me what to do. So I had something else about component-wise analysis, but that might take a bit long. So that would be an analysis of different components of a transformer architecture, what different components contribute to the decrease of the loss function. And we also try to analyze this for translation models and language models.
I think this sounds interesting.
Maybe I can start with that and then see if you want to drop out, you can drop out anyway in any point of time. But
can I ask you a very question about the stuff before? One very general question and one slightly more narrow question.
Yeah.
So the general question was about the system you talked about for multilingual translation. Would that kind of system work, for example, with multilingual Wikipedia? Would it be suitable to doing a multilingual Wikipedia project? And the narrow question is about this work you presented about the attention patterns, that sometimes you can fix them, and that's of course saves you, especially with resource poor languages, and you can reduce the computational burden. So would there be some way to smoothly interpolate between the two? So you have an optimal trade-off between using partly fixed and partly learnable attention.
Yeah, so I was very quick on that. So that's basically what we did also. So there was still one attention head that was trainable, and that was also quite important. So in the end, it didn't make a lot of difference, but you could see if you, for example, analyze the effect on translating longer sequences, then this trainable attention head was really important to keep the accuracy up for also longer sequences. So you need to have maybe some additional kind of attention mechanism that needs to be trained and optimized. So in that sense, this was already a trade-off between 7 fixed attention patterns and 1 trainable one. And then you have this on each layer also. So you would have basically 6 learnable attention heads for the entire encoder, whereas the 7 of them would be fixed and just give access to certain positions. So in that sense, this is already the trade-off. And maybe this could also, of course, give you some more systematic ways of making even more trade-offs between different setups, but that seems to be the beneficial setup for us. Why you need 8 attention heads and not 12 or 16 is also an open question, of course. Yeah, and whether those patterns are now the ones that are the universal patterns that you should need and nothing else is also still an open question. So I think there might need to be some more studies on that as well. Then the first question, let me see if I understood that. So Wikipedia, what do you mean by work with multilingual Wikipedia? Do you mean like, can that be used for translating Wikipedia, or can it be trained on Wikipedia data, or what was exactly that?
No, creating Wikipedia. I mean, there is, from what I understand, there is a open some kind of a Wikipedia project which is multilingual Wikipedia. Namely, maybe there is some content created in one language, and then you automatically create that content in other languages as well.
Yeah. No, so we have been actually working together with the Wikimedia Foundation to some extent. So they were interested they already used machine translation to bootstrap pages for other languages. And they were especially interested in pushing smaller languages. So they wanted to have machine translation integrated in this kind of editor mode that they have, where you can pre-translate certain pages from English, for example, into a smaller language or less resourced language. And you could use a free editing mode for adjusting it to that language. So I don't know if this is exactly the same kind of project that you're referring to, but they are very much interested in better coverage for smaller languages. And that definitely is also some idea that we would have to push more for coverage of languages that are otherwise not well resourced. And for example, translating information from Wikipedia or other wikis would be a typical application area. Yes.
Yeah, thanks. That was the editor was exactly what I was referring to.
Yeah. So no, so the models that we have can be used there already. I think they have integrated neural machine translation as one of the modes that you can use in this editor. And we had some pilot project with people from the Wikimedia Foundation.
Do you know how that compares to other ways of doing it? For example, you know, that we have at Chalmers the grammatical framework thing that also does multilingual. In this editor mode. Have there been any comparisons of how well the two different approaches work?
I don't have a systematic comparison, but so of course, neural machine translation is always depending on data. So if there's little data, then the system does not perform well. Multilingual models then try to push that by doing perfect or some kind of transfer learning. And that pushes a little bit, but we also, for example, we have been working on Northern Sami, which has very little data, and that you can really do a lot with data augmentation, and you can also, for example, use the information from rule-based systems to create data sets that can be then piped into data-driven methods like neural machine translation to push the performance for those. And we did some kind of comparisons, and then you can see that maybe some model that has been created manually by experts works very well for certain kind of language that they are optimizing the grammatical analysis for, but it might not be as robust if you have some kind of a new input coming in. So it's difficult. Evaluation in machine translation is a difficult topic in any case, but I don't have really systematic comparison.
Thanks.
Yeah. So I'm not really sure how to go about with anything else that I could present here, as this now kind of the hour is gone already. I can flip through some slides, and if you see something interesting, you say stop.
I think for us, it's fine if you want to speak for a little longer. Okay. I'm sure some people perhaps will have to go elsewhere.
Yeah. Yeah. I'm sorry about my time management, really not good. But okay, I can quickly just say what this is all about, and then just say that you can analyze, for example, different components, and then we don't have to go into all details, but I just give you just a picture, and then you might ask me later or contact us later also. So, but this loss change allocation is interesting because you can analyze the learning dynamics of transformer models, for example, and component-wise see where does the improvement in the training objectives come from. Actually, what kind of contribution do you get from different components? And that's what we wanted to see. So maybe don't look too much at this kind of more explanation what LCA is, but so now the main blocks that we have in transformers. So you have some kind of attention mechanism, which is of course an important thing, and then you have this feed-forward block, and you have those different components there that need to be trained, and you can now see what part of the network and what kind of part of the which component is really contributing now to a decreased loss in the training procedures. Now this picture, for example, and our main interest was, is there a difference between typical language model tasks and a machine translation task, just to see is there something really different going on. And here's basically one of the slots of plots that you can look at, aggregating over all these training steps and all attention heads, for example, and then you can see what the components of key query value are contributing to the loss function. And for example, the different components of the feed-forward block, how they contribute. And so actually it's good. I don't have really good answers to the difference that you see here, but you can see that something is happening on different layers, and that might be an interesting thing to explore a bit more. So just quickly saying that it seems like a lot of contributions at least visually, seem to come from the feed-forward block, but that might also be a bit misleading here now. But you can see that this kind of feed-forward block is reorganizing information maybe, and then a lot of loss improvement comes from that kind of block. We also see that kind of shape, which is interesting. So if you're interested in why do you have that kind of shape, and we don't have good answers for that, but you see also that it really differs between the different training objectives. If you have a masked language model, the blue one, then you see that there's really some kind of drop in the middle layers. So the middle layers don't seem to really contribute a lot, which might say something about the architecture, that somehow there's over parameterization there, possibly. But it's interesting to look at those different shapes. So why does it happen now that we have a very large peak at the final layer? Maybe makes sense to make the final predictions. You need to adjust a lot there, but the middle layers seem to be very much underperforming in this loss optimization. Whereas if you look at, for example, the machine translation model, then it seems to be that more like the entire network is contributing more uniformly to increasing or improving the loss function. So that seems to be across the board one of the things that we observed. By the way, here, this green stuff, you can see that there's also a clear difference between encoder, decoder. We just put them together now, but you have the encoder in the light green and the decoder in dark green. Surprisingly, you can see that the kind of attention mechanism seems to be very similar in encoder and decoder, even though the decoder operates quite differently in a machine translation model. You're masking the future context and so on. And then the causal, like a predictive or autoregressive language modeling, then it's somehow in between the masked language model and the translation model, which might make sense if you look at that the decoder of the machine translation model is basically the same as a causal language model. So also might be interesting, but I don't know what to conclude from that exactly. Is not entirely clear. Just also, you can verify that the same kind of trends more or less happen in different language pairs. So as this is one language pair, this is several language pairs. And yeah, so as I said, I want to just do this quickly just to give you an impression. And you can also look at over time. So this would also be interesting to see what happens during training time. So if you look at the different contributions during training, how do you observe what the different layers do at each training step? So you can really in a detailed way, analyze all the contributions to optimizing the loss function. And you can see a typical kind of fading out at the end, but you see that the contributions are really different in different layers at different steps. In the beginning might be some warm-up time, then you have a lot of contributions, and then it fades out. But again, you see that the middle layers, not much is actually happening. The main thing is in the beginning at the end. Maybe I should skip that plot. Just want to show you nice, colorful plots. But yeah, well, this is basically distribution over attention heads. Just to point out also that do we see any kind of specialization of attention heads? And this also is confirmed by other literature that some attention heads seem to do some heavy lifting, some others are less contributing. But in the end, the contributions are still very much distributed. But you can see some dark spots here, which really indicate that some of the heads do a very heavy lifting and improving the loss function, whereas others are not very active. Okay, I think I should wrap up. And maybe just those kind of very vague conclusions. In the end, I didn't tell you much what we actually can conclude from this. So the main conclusion we can draw is that indeed machine translation and language models are different. You can see differences, how the training objective is influencing how model components are contributing to the training objective. You can see differences in contextualization. You can see different ways how the embedding space is developing. And it seems to be quite clear that it's not a universal way to get to some kind of representation, but it really depends a lot on the training procedures that you're using. So it's not very well, I don't know. Interesting conclusions are difficult to draw because it's very difficult to generalize. So one question is, of course, what are the consequences? I think we touched a little bit on that. So I would basically ask you if you see any interesting analysis that could really influence or impact development of future models. So I could see that, for example, maybe that influences architecture design, how they should be designed for perfectly learn some kind of task. Can we see from those patterns maybe some ways of improving models? And also hinting on that you should be careful on what part you use and how do you make conclusions about representations if you don't really carefully understand what the embedding space looks like and so on. Yes, I think that's, maybe I can say that. So I think what started us in this direction was basically also that it was not easy to use a generic language model as an encoder for translation. So that was a bit puzzling. You could think that, okay, language model is useful for so many different things, but it was quite difficult to turn that into a decent encoder for translation tasks. So maybe the analysis hints on the differences that make it difficult to just use it as an encoder. And this paper, if you're interested in that, tries to figure out a little bit more how to turn, for example, a BERT model into an encoder for machine translation, just as that component. And there are techniques that you can align certain spaces and fine tune to change the representations in a way that they become useful for machine translation. Okay. Yes. I stop basically here, don't say much about that, but this kind of is the setup of the project. So we are looking at further exploring translation models and analyzing them. So this kind of sub-project 2, which is about interpretation, is mainly what I was talking about. So how do we interpret the representations? What do they cover and what do they do? We work on developing models that can scale up. So that's what I presented in the beginning. And we look at machine translation as one downstream applications, but then also other kinds of downstream applications where we can measure the ability of understanding language in a meaningful way. And I'm sorry for the rush at the end, but thank you all for your attention. I'm definitely willing to stay here if there anyone wants to discuss more. Here are some of the people who did the actual work, postdocs and PhDs who work on the different things that are presented here, and I would like to thank them and also the entire Helsinki team, and of course also the funders of the project. So I stop here. Thank you.
Thank you, Jörg. The loss allocation. How is that related to vanishing gradients? Is it related?
I don't think it's related. So it's more about analyzing where the contribution comes from. So what kind of component is contributing to the loss optimization. So let's see, is there vanishing gradients? Is there some?
I mean, if you do train with it's a gradient optimization. That's how we train a neural network. And in deep networks, that is a problem. That's sort of the early layers. They don't affect the loss function as much. So if it's calculated in a similar way, or if it's based on the gradient, then perhaps that has some that plays into it.
Okay, yeah, I didn't think about that actually. So, but that's an interesting point. So we should think about that more carefully. So you mean that could be the effect that we see here, so that so we just kind of see a proof of the vanishing gradient problem inside of a deep neural network. Is that what you mean?
I'm not sure I understood exactly what you did, but I think the conclusions were that sort of some layers further into the network has a greater effect on the loss, and that effect is measured as changes in the weights or changes in the representations.
No, it's the gradient that is used for computing that kind of contribution to the loss function. So you kind of decompose how the kind of loss optimization is done with the the method that you go along the gradients in different dimensions, and you can see which dimension is then really pushing the improvement. So you can measure that then what kind of parameter is really contributing a lot to improving the loss at each step. So that would be a decomposition of the loss function, basically distributing it over all the parameters that you have, and you can, while training, just observe this, basically dump that into some way that makes you makes it possible to analyze it afterwards. But yeah. So is that a known fact that you have this kind of problem in training transformers, that you have in the middle layers some kind of vanishing effect?
Well, the vanishing gradient is an effect on deep neural networks in general. I'm not sure how, but I wouldn't think that transformers are immune to it.
I remember that only from the discussions of like the early recurrent networks, and then the kind of LSTMs came in to actually address that problem.
Exactly. And LSTMs address it to some extent, but then transformers they address it even more, because you have a shorter path from the loss function to each token in the input, but with the attention heads.
And then of course you have even the residual connections that also make even more kind of shortcuts. So I'm not really sure how much that is also affecting the entire network. I guess they're quite important. Otherwise, why would they be there otherwise?
Yes.
But good point. Maybe that. So do you have some kind of reference to some paper where they discuss vanishing gradients in transformers?
Actually, I don't. So I was just thinking on earlier papers on this, but I can look into it and see if I find something.
Yeah, please go. I mean, that would be interesting to understand. So maybe that's just but on the other hand, if you look at the machine translation model, then you would not see that effect that the middle layers still contribute a lot. So there we didn't really see that effect. It's still the same kind of transformer model, but of course it's also maybe the division into encoder, decoder, which has quite different functions, which makes it behave differently. I don't know. But then also, if you go back to the picture, there's this weird effect for causal language models, which are in the middle quite active. And then at the end actually fade out, which I don't know is quite different to what the masked language model is doing for some reason. I don't know what is happening there. Then I mean, the feed-forward network, I can imagine that this just builds up on top of each other, that maybe each layer becomes more mixed information that needs to be reorganized. I don't know if would that be an explanation, that you then in the end, this kind of reorganizing of information that accumulates things from each layer has a heavier influence on the loss function? And that's maybe what you see, this kind of cumulative effect of layers stacking on top of each other. I'm speculating here.
Yeah, no, it's really interesting, I think. Do we have some other questions? There are some people left in the meeting.
Yeah, so there was an early question by Björn Gambeck. I didn't address that.
Yeah, so that was regarding to the question I asked in the beginning with similar languages and similar languages.
Yeah. No, so I mean, I didn't want to make a claim on kind of similarity or what languages are more distant. Maybe this was not the, of course, social contact between Finnish and Swedish was big, which makes it very, there's a lot of impact on the languages. There was more like a typological difference maybe, but maybe that's not the important thing. It's a fair point. Maybe I should use some other examples.
All right. So thank you very much for this interesting talk. I learned a lot. Next week, there will be no seminar, but the week after that, October 13th, we'll have Tomas Trzcinski visiting us. He's been working a lot on continual learning and generative modeling, and also on data from the Large Hadron Collider. So I think that's going to be exciting as well. Thank you for today.
Yeah, thanks a lot. I'm sorry again for being late. I mean,
don't be.
So much time.
Don't be. It's
okay.
We don't have a fixed ending time, and I think this was really exciting.
Okay. Thanks for listening, and thanks for organizing it.
Thank you. Bye-bye.
Bye.